Well, good evening and welcome back to the second stochastic session. Right, so for the first 2 hours is going to be maths, and then we come on to do the number crunching. And what we're going to do this evening is essentially two things to do with stochastic differential equations. One is manipulating stochastic differential equations, so that means further Ito, i.e. continuing from what we did the other day. And the second part is going to be simulating stochastic differential equations, which means the numerical side of SDEs. You can't really solve stochastic differential equations by hand, apart from a few well-known classic examples, which we'll go through. The majority of SDEs have to be solved numerically because they're too difficult. So we're going to be doing both of those. So we just have a quick look through these bullets that Paul's provided. In this lecture, further use of Ito's lemma to manipulate or solve stochastic differential equations, which means we went as far as Ito 1 and 2 the other day. We'll do Ito 3 and 4 and see how we progress. Then we'll look at continuous time stochastic differential equations as discrete time processes. But before that, there is actually another bullet point, because you'll see that there's another topic in there, and that's going to be further Kolmogorov equations. If you remember the observations part of the very first session that you had with me, it said that later on we'll look at financial quantities, because the Kolmogorov equation we looked at the other day wasn't actually very complicated. So what we'll do is we'll extend what we know already to look at Kolmogorov equations, not just to look at Brownian motion, but where there's drift and diffusion. And you'll see exactly what I mean shortly. So as far as the maths is concerned, it's really these two. And everything beneath that red line is going to be all the simulation stuff. So the top bit is manipulation of SDEs. The second part is simulating them. So continuous time SDEs, discretized, in other words, written down as discrete expressions. Then we'll look at simple ways of generating random numbers in Excel, so the mathematics of random number generation in Excel, and we'll finish off with how to correlate random walks. And then after we do that, we'll then do the actual laptop session. So that's what we're doing this evening. Let's make a start then. So the idea behind this lecture is to look at more methods for manipulating stochastic differential equations, finding transition PDFs for arbitrary stochastic differential equations. Right, so that's the second part of the maths. And then everything that follows from that point, probably after the break, will be simulating SDEs. So we're going to be doing both maths and numerical methods this evening. Right, evening, all our distant folks who are just saying greetings. Right, what does it say? It says, in order to become comfortable with the kind of models used in quantum finance, we have to get a good understanding of stochastic differential equations. So now you've seen from a few classic SDEs at the end of Tuesday's session that most of the work that we do is going to be based on studying SDEs. The reason being that if you're going to do things like pricing derivatives, you have to know precisely what the underlying is doing. And in order to do that, we use asset price SDEs. You saw a couple the other day, and over the coming months, you're going to see lots and lots of different examples. So a quick recap. Here's an SDE. So let's start off by saying G as a function of t is a stochastic process. And what that equation tells us exactly how G evolves as we go from one time step to the next. In other words, as we go from t to t plus dt, this is what G looks like. So remember we said that we can either call this a stochastic differential equation for G or a random walk for dg. Whether we say an STE for G or a random walk for dg, we're talking about exactly the same thing. And notice each part, that has two components. Before the plus sign, that's the deterministic part. After the plus sign, it's the random part. The very first part consists of two bits, the drift times dt plus the diffusion times dx. Obviously, the larger b is, the more fluctuations we're going to see. So it's called an STE for G or a random walk for dg. And remember, if we can write down the evolution of any stochastic process in this form, then that is called a diffusion process. That's the special name we give to it, or the status. Right, so A is deterministic. B in fact is also deterministic. The randomness is really coming in from the dx bit. Right, so if remember when we said that if we open this out, it was actually equal to G at t equals G naught plus the integrals here. And we saw on Tuesday we can write down any STE either in differential form or integral form. And we say that G evolves according to this process, or this STE. That's the STE which models the evolution of that process there. Is everyone happy with that? Or is there any bit you'd like me to go through again before we move on? So equation 1 represents something we saw the other day. Geometric Brownian motion. Remember, we said it was the most commonly used recipe for generating asset prices that can't become negative. We said this the other day. We switched off the randomness, right? And we showed that in the absence of randomness, that the drift part was something that could never become negative. Remember, it was of the form e to the mu t, wasn't it? So this is a recap of what we did the other day. That's the most basic form of Ito, remember? We did two forms of Ito the other day. One where we've got a function of Brownian motion, and one where we've got a function of both Brownian motion and time t, remember? So we did Ito 1 and Ito 2. Now, let's think of Ito 3. All right, so I'm going to find a blank screen, because we're now going to move on. Let's suppose we've got a stock price. So here's a stock, S as a function of t. And remember, this evolves according to geometric Brownian motion. Remember, whether I write it like this, or I take the S across, it's really the same thing. Agreed? And I've got a sum function of S. Consider a function V as a function of S. And S changes by a small amount. The obvious question to ask is, what's happening to V? So let's go back and use a Taylor series expansion. So Taylor gives us V of S plus dV by ds plus a half d squared V ds squared. And we'll stop there. We'll stop at that point for the reasons we mentioned the other day, that after that the coefficient, the orders become smaller and smaller. Remember, we're only going as far as anything that's attached to a dt term. So if I take the v on the other side, that gives us dv, agreed? So dv is equal to dv by ds plus a half d squared v by ds squared. Now, we know what this is. that's this thing here. Agreed? What about ds squared, though? ds squared. That is equal to mu squared s squared dt squared. Plus, we've also got a sigma squared s squared dx squared, which is a dt, right? Plus the cross term product, which is 2 mu sigma s squared dx dt. That's what we've got. So what we're doing is we're trying to figure out what this ds squared looks like. So let's have a look. The very first term here, in or out, do we keep it or do we get rid of it? We drop it, right? Because it's too small. Get rid of it. This we keep, obviously, agreed? Because we've already said the dx squared became dt. What about this? What should we do with that? Do we keep it or do we get rid of it? And together with a reason for your choice. What's the size of dx? Root dt. So what's the overall size? dt to the 3 over 2. So is that smaller or larger than this? It's smaller, right? When dt becomes very, very small. So we get rid of that as well. So all we're left with is the diffusion squared times dt. So if we mention, the reason why. Oops. Because it's order dt to the 3 over 2. So that goes. So we can say, right at the end, ds squared is sigma squared s squared dt. So let's replace ds squared with that and replace ds here with this thing there. And if we then group all the dt terms together and all the dx terms together, we then get what I'm going to call Ito3. So therefore, dv is equal to, brackets, mu s dv by ds plus a half sigma squared s squared d squared v by ds squared dt plus sigma s dv by ds dx. And there's our third form of Ito's lemma. In other words, you've got a function of a stochastic variable, like a stock price, which follows its own stochastic differential equation. And you want to find out what the change is in a function of s. We use that then. Can you see this is also a stochastic differential equation? The bracket before the dt is the drift, and the sigma s dv by ds is the diffusion. So let's call this Ito3. Drift and diffusion. This is another stochastic differential equation. So what we've done essentially here is we've gone through everything over here. In order to obtain equation 3. That's what we've done. So let's use that for a very important example. So, very important example. What we're doing here is we're assume sigma and mu are constants. You may come across another way of writing this in a book, so don't get put off. Another way of saying that these are constants is simply to say, or if you want to make it quite clear that you're taking something which is positive, just stick a plus in the front. But if in any book you come across, it says this, that's just simply a flashy way of saying that the mu and the sigma are constants, rather than variables. So what we're going to do is, we're going to get a solution for geometric Brownian motion, for the special case where the parameters, the mean and the standard deviation are constant. And it only works for that particular case, no other case. But the fact that it works means that we should look at it. And I said at the beginning that most stochastic differential equations, practically all of them, have to be solved numerically, but the few that can be solved, that have a closed form solution, i.e. one that you can do by hand, you attach a lot of importance to. So that's what we're going to do. And the way we're going to do that is we're going to do Ito3 on the function log s. So we do Ito3 on log s. Right, Michael is saying, I missed it the other day, but can you go with a big O notation how we just got to 3/2 with the second term from the previous equation? Right, you need to ask me a specific question when you say, can you go over it? What I'm saying here is that this is of size dt to the 3/2, because we know that dx behaves like, well, let me write it down. We did this on Tuesday, in fact. We know that dx is phi times root dt. So in other words, we can say that dx behaves like this. But then you've also got that multiplying with a dt. So the overall magnitude of that is going to be dt to the 3/2. Right, so that's the question that's being asked. Right, so shall we do that? That means what we have to do is we have to substitute dv by ds in the second order derivative into the previous equation. And if we do that, let's see how much there is here. Right, so I think what I can do is I can squeeze this into the line above. So what we have here is we've got dv is equal to mu s times dv by ds, which is 1/s, plus a half sigma squared s squared times minus 1/s squared, times dt, plus sigma s dv by ds, which is 1/s, times dx. So we find that there's a lot of cancelling going on here. And we also know that dv is equal to d of log s. So that's where this comes from. After you've done all the cancellation, you're left with this. Right, so is everyone happy with that now? Everyone happy where that's come from? What we're trying to do is, from this, we're trying to capture s. If we capture s, what we'll then get is a closed form solution or a formula which allows us to obtain different values for s. That means in order to get the s, we somehow have to kill off the d in front. So the obvious thing to do is integrate. So we choose a time horizon. We choose a time horizon between, say, now and some time in the future. And in this case, what Paul's done is he said today is time t is equal to 0, and he's going to do it, integrate between now and some time in the future, little t. Right, so that's what's happening over here. So each of these terms is being integrated. Now, when we integrate the left-hand side, what does it become? It becomes log s at t, so it becomes log s at t over s at 0. Agreed? That's what the left-hand side becomes. The right-hand side, the very first term, mu minus a half sigma squared, that's a constant. So we can pull that out, and what we're left with is a dt, so we integrate that, we get time between 0 and t, so it simply becomes t minus 0, which is t. That sigma comes out, and the integral and that d gives us a Brownian motion at t minus x naught. We know x naught is 0 anyway, but this is what we end up with. Are you happy with that? So the left-hand side is relatively straightforward. Sorry, the right-hand side is relatively straightforward because we've got mostly constants. So once that sigma on the right-hand side comes out, this comes out, what we then got is this. That's it. And that's where the expression comes from. So x naught, whether you leave that as x naught or you say that, well, that's actually 0, it makes no difference. Are you happy with that? Now remember, we're trying to capture, given today's stock price, s at 0, we want to work out the stock price at some time in the future, at time t. So obviously, if we take exponential of both sides and take the s naught across, we then get a formula for st. So that's what's happening, and that's what we end up with. We can also write this down as st. St is s naught e to the mu minus a half sigma squared t plus sigma times phi. What should I multiply the phi with?
Root t. No, sorry, root t.
The square root of t. The reason being that this has to have a scaling depending on what the time jump here is. It's 0 to t, so it's t. So it has to be the square root. So what I'll do is I'll write down a couple of other examples. Suppose instead of integrating between 0 and t, we integrated between t and t plus delta t, or dt. So let's go to a blank screen and fit that in. So let's do that here. So case 2, that was case 1. Case 2, we now integrate over t and t plus dt. Let's say delta. Should we say delta t? The solution then becomes the following. So again, note how the drift scales with the time step, whereas the volatility scales with the square root of the time step. Case 3, another example. Integrate over 0 and big T, in which case it becomes st equals s naught e to the mu minus a half sigma squared t plus sigma phi root big T. So that's really just to give you an example of how the time over which we integrate affects the solution. Now, case 3 is particularly useful if you're pricing European options. With the European options, remember, the payoff depends on the stock at expiry. We're not really interested with a European option or what happens in between now and expiry. All we're interested in is what happens at expiry. So what you could do with this formula is generate a whole load of stock prices in the future, like this. So here's S naught, and here's ST. So what you could do is one price there, another price there, then you've got, let's do some other colors. Color hasn't changed. Let's try that. Another one there, and so on. So what we end up with is a distribution of stock prices at time big T, and then we can simply work out the payoff and work out the price of the option from that. So you don't need to with this, do a whole load of these, or that, or another example, this. We just simply simulate all of these prices at expiry. Obviously, when we come on to do things like path-dependent options, then it's not so straightforward. We have to worry about what happens in between. But this is particularly useful if you're pricing non-path-dependent derivatives, because you can do one gigantic jump from today, which is today's stock price, at time t equals 0, to time big T. So really, I should simply write down just big T there. All of these values here are S at big T. Right, so that's your first real example of manipulating stochastic differential equations. Now, have a look at the form of this solution. Can that ever be negative? Now, remember we did this the other day by switching off the randomness. And I said that when we bring the randomness back in, we'll still get something that can't be negative. There's the full solution. Okay. Michael Patterson is asking, much better with the European options. What about barrier options, since those are also prefixed timestamps? Well, barrier options are examples of exotics, so they're path-dependent options. So you wouldn't want to be using one gigantic jump. So you can use this, of course. I'll do step by step. Now, shall we look at an interest rate? We saw this the other day, and I described some of the dynamics of this model. So let's write it in exactly the same way we had it earlier. Remember, we wrote it this way. Now, let's go about solving this. What we want to do is we want to try and capture the I. So the reason why the Vaschet model is nice is because, again, it has a closed form solution. So let's go about solving this. Let's have a quick look what's on the next slide. Let's do a transformation or a substitution. So let's write down that U is equal to R minus R bar. In other words, on the previous slide, over here, we're saying that this is equal to U. So if U is equal to R minus R bar is fixed, that gives us that du is equal to dr. Agreed? And what we end up with is this nice looking smaller formula or stochastic differential equation given by this. Now that's a famous result in mathematics or theoretical physics. Anyone recognize that? I'm sure Michael will spot it. Anyone here? A well-known equation. That is, anyone heard of an Ornstein-Uhlenbeck process? Anyone come across that name? It's quite well known. And the reason why people like Vasicek is because it can be reduced to this form, and this can be solved by hand. So this is called an Ornstein-Uhlenbeck process.